Sue, Judy here. I don't know if you can hear me. How do we get the audio so we can hear you?
Can you hear me now, Judy?
Yes, I can. Thank you.
Okay. No? Okay, we might make a start. Tēnā koutou katoa. Thank you very much for coming today to our 4th seminar in the Deep South Challenge seminar series. It's actually the last for 2017 as well. But we'll be hopefully kicking off the series again next year with taking a look at old weather records and what they can tell us about our future climate. Sorry, just a second. So the Deep South Challenge, for those of you who don't know about us, are tasked with supporting New Zealand to adapt, manage risk, and even thrive in a changing climate. We actually have something like 35 projects across the full spectrum of climate science and adaptation research. And one of the challenges of running such a broad program is maintaining and developing collaborations between such a diverse range of projects. So these seminars are one way of keeping our projects in touch with each other, but it's also a great chance to invite interested members of the public and stakeholders, iwi and hapu from across the motu, to take a closer look at some of the detail of our research. So first of all, I want to welcome those of you who dialed in from your desk or at home, and also to those of you who've made your way to your closest physical hub. We're here at Victoria University in Wellington. I think today we might have a bunch of folk from NPI. They've set up their first physical hub, so a special shout out to you. And a reminder that if you are at a physical hub, please sign an attendance sheet so that we know who's coming and who's interested. A little bit of housekeeping for those of you who haven't used Zoom before. Please keep yourself muted and don't be offended if we mute you. We'll leave about 15 minutes at the end of the seminar for questions. When it comes to question time, if you've zoomed in, you can raise a hand via Zoom, clicking on a little icon on the right of your screen. If you're in a physical hub, just raise your hand and the organiser will raise the hand of the room on Zoom. So finally, I want to thank Suzanne Rosier for coming along today, all the way from Greta Point. Suzanne is a climate scientist at NIWA in Wellington. She played a key part in helping launch Weather Home Australia and New Zealand back in 2014. And she subsequently analysed the large data sets coming from New Zealand with a particular focus on extreme rainfall. Her new Weather at Home Australia and New Zealand experiments are looking into how weather and climate extremes might be different in New Zealand a few decades from now. So without further ado, I will get your slides. That's all good? Yeah. Thank you. Good afternoon, everybody, and thank you very much, Alex, for the introduction. It's a real privilege to have the chance to speak, and thank you very much for your time in coming along and listening. I'm hoping to convince you that Weather at Home ANZ is a very powerful tool for giving us information about how New Zealand's climate is changing and how much of that can be attributed to the human influence on climate, and also telling us something about how climate and in particular weather extremes might be changing in the future. Don't worry, I'm not going to read all of these out to you, all these names, but there are an awful lot of people who have
helped me with this project. Too many to name here, but basically Weather Home ANZ has been a collaboration mostly among Oxford and the UK Met Office, NIWA in Wellington, and the Universities of Melbourne and Tasmania. So a lot of people to thank for help with this. I work part-time while I'm raising small kids. I work 3 days a week, and I'm very grateful to the Deep South National Science Challenge for funding me 2 of those days a week, and also, of course, NIWA, who fund me for the other day a week. I'm also hugely indebted to Nessie and the guys who run the HPCF at NIWA in Wellington, who do a fantastic job of curating the huge amount of data associated with this project. So in preparing the talk, I found myself thinking about the Deep South mission, which is to enable New Zealanders to adapt, manage risk and thrive in a changing climate. And I thought to myself, well, to thrive, we need to know the risks so that we can plan how to adapt. And I found myself thinking, what are the risks that matter to New Zealanders, and in particular, what are perhaps the most immediate risks to New Zealanders? So in essence, my research focuses mostly on how we get from this, which I'm sure you're all familiar with, global warming. What is that actually going to mean in our everyday lives? How do we get from something like this to something like this? Landslip, this may be familiar to some of you. It was only a couple of months ago in Wellington, around about the same time that Hurricane Harvey was pounding Texas, but we had some very, very heavy rainfall here, and of course, as well as flooding, landslip is quite an issue for New Zealand, as I'm sure you're aware. A couple of years ago, this is what Dunedin looked like in June, so we've had various of these very heavy falls of rain recently in New Zealand. And of course, to my mind, the other perhaps most immediate problem is at the other end of the rainfall spectrum is drought. So I had to think, my work is trying to focus on getting a handle on potentially changing risks of the effects of climate change that will most immediately impact our lives here in New Zealand. So I believe drought is most costly to the economy overall. Extreme rainfall, of course, there's also extreme wind and storm surge, and of course, if anybody has any particular thoughts on other things, very, very happy to investigate those with the project as we can. Of course, there are plenty of other things in store too with climate change. The more slower changes in mean climate and sea level rise, but they do give us rather longer to plan for those. So with Weather at Home, I've tended to focus on these things which will have the most immediate risk to New Zealanders. And final slide of the introduction, just to I thought a rather nice illustration of changing climate effects. This is a sort of hypothetical distribution of temperatures, where the solid line is without climate change, and the dotted line is how it has changed with a change in the climate. So in the top here, we see a shift in the mean temperatures overall. If the distribution were to stay essentially the same shape, then a systematic shift in the mean automatically implies you would expect more extreme hot weather and less extreme cold weather. But of course, as we see here, you could equally have a situation where the mean actually stays the same, but the variability increases. Or you could have some complete change in the symmetry altogether with the mean staying the same. Weather at Home is very well positioned to help us investigate things like this, because it essentially creates very large ensembles of model simulations, which means that we get better statistics and more reliable ideas of these distributions of various climate metrics. So that's really one of the great strengths of the Weather at Home project. Okay, so that was just introduction. Here's an outline of the talk. I thought I'd start by just giving you a little bit of background about climateprediction.net, which Weather at Home is part of. And then since a lot of the work we've done for New Zealand climate has focused on the attribution issue, I thought I would just say a few words to be clear about what we mean by attribution and FAR, which is a commonly used metric in attribution. Then I thought I'd give you a brief roundup of some of the New Zealand science we've done with the output, and in particular I'll talk about a July 2014 extreme rain event that happened in Northland, and then say a little bit about current work that we're doing, and another way of using these FAR attribution estimates, where we've been looking at the estimating financial costs of climate change, and then finally 2 sections which are looking slightly ahead to the future of this project. One is impact attribution, and one is using Weather at Home to say something about how climate extremes might be changing in the future. Excuse me. Okay, so a little bit of background to Weather at Home. I know this will be familiar to some of you, but perhaps not everybody. So just to be absolutely clear, Weather at Home runs as part of climateprediction.net, or CPDN for short, which is a global volunteer distributed computing project. And back in 2003, less than a handful of very clever guys in a basement in Oxford figured out how to make a fully complex global climate model, state-of-the-art scientific model, make it possible for that to be downloaded by anyone in the world who has a PC and an internet connection. The original idea was Miles Allen in Oxford, although it had already been this sort of harnessing of volunteer computing power had already been around with SETI, the Search for Extraterrestrial Intelligence. So it was launched in 2003, and many tens of thousands of generous volunteers signed up and continue to crunch the models. It mops up spare processing power on your computer, so if you volunteer, you shouldn't notice any difference in what you normally use your computer for. It automatically harnesses that spare processing power. The point about it really is that the amount of computing power that's harnessed in this way is absolutely phenomenal. Scientists, with these fully complex climate models, scientists are normally happy if they can run them maybe a few tens of times. But climateprediction.net manages to run them literally thousands and thousands of times, which is why we can build up those more reliable statistics, and why in particular something like Weather at Home can say what it does, because extreme events are by definition rare, so we need lots and lots of simulations in order to capture the very rarest weather. So for the first few years, CPDN ran global models. And then in 2010, it launched Weather at Home, and this is what we've got in Weather at Home. Essentially, inside the driving global model is a limited area, which is modelled in much higher resolution, high enough resolution that we actually capture weather events. So that, together with the fact that these models are run many thousands of times, means that we can look at how weather, and in particular extreme weather, are changing. I should also say it's an atmosphere-only model, so we supply it with sea surface temperatures, SSTs and sea ice at the bottom. It's got 19 levels in the vertical. So here's our domain for ANZ. We managed to cover much of Indonesia as well. By regional modelling standards, it's actually a very large domain, which means that we can only manage to run it at 50K resolution, which for New Zealand precipitation is a little bit of a shame. It would be nice to have, there are some challenges for something like precipitation in New Zealand, but all the same, there is a lot of useful information there. One thing that's possibly on the horizon is it would be extremely nice if we could just cut out New Zealand and have a New Zealand only Weather at Home, in which case we could have super high resolution. So, and that's something that's a possibility we certainly keep our eye on for the future. So really we're limited by storage. This project produces vast quantities of data. Once we release an experiment, we get back about 1 terabyte a week. And really the only reason we end up calling a halt to how much we collect is literally just storage space. And the way it works is that the scientists so far at NIWA, Wellington and Melbourne have put the experiments together. It's Oxford who releases those to the public, and then our results actually return to a server in Hobart at the University of Tasmania. Weather at Home launched in 2010 with 3 regions, which were all launched from the project base in Oxford. We here in ANZ were actually the first region to be successfully launched remotely from the project base, so that was rather neat. And as you can see, Weather at Home in Oxford is now modelling 15 regions, and as time has gone on, I think the need for those, or some of those regions, to actually supply their own servers to store the data has become greater and greater. So Oxford still releases is in control of releasing all the experiments, but more and more the results return to a server in the country of interest. And finally, if you choose to take part, this is just an illustration of some of the graphics you can choose to see. You can actually track how the model that you're running on your computer is evolving. And finally, just ClimatePrediction.net is a truly global project. There's a black dot on this map for somebody in the world who's running CPDN and volunteering their computer in this way. As you can see, it's mostly concentrated in Europe and North America, but there's somebody in all 4 corners of the world, including right down where we are. Okay, so that was just a bit about CPDN. Then I thought I'd just say a few words to be clear about attribution and FAR that we use to measure that. What do we mean by attribution? Well, essentially we're looking at, we want to get 2 estimates of climate. Could be mean climate, doesn't have to be extremes, but extremes as well. We're essentially looking at how they are or would have been with and without the human influence. So we're looking to say something about how those have changed. Have they changed? If so, how? And what, by how much can we attribute to the human influence on climate? Generally speaking, we do tend to use models to do that because we can run those models under controlled conditions, whereby we can run them with the anthropogenic or the human influence, and then another stream of experiments where we take that away. We can use observations, however, but it requires a relatively long time series of good quality observations, and we need a long enough time series that we can effectively have an early climate period, and a late climate period, and compare the 2. So that tends to be more successful for temperature studies. We don't tend to have such long or high quality records for precip, which for us in New Zealand is not as ideal, because personally I tend to think that a lot of the ways we'll feel the most immediate impacts of climate change is through precip in one way or another in New Zealand. So usually we choose to use models for these purposes. If we are using models, then validation is crucial. We need to stay always rooted in the observations, make sure that our model does actually reproduce the event or the conditions that we're looking at. And in particular, if we're addressing extremes, then it is still very much an open question in this part of the research field. Something like Weather at Home, which we run thousands of times, can tell us something about the 1 in 5,000 year rainfall event. But if we've only got 100 or 50 years of measurements, then we only know about the 1 in 50, what we've observed can only tell us about the 1 in 50 year event. So, and that is still very much an open question in the research community about how exactly we validate those extremes. And this, to my mind, is really the core of climate change attribution. This is quite an old slide now, but still very relevant, and to my mind also the guts of any rebuke to a climate skeptic. This is 1850 to 2000 across the bottom. red is the observations and grey is the models. And in this panel here, we've only forced, the models were only forced with natural forcings only, and you can see that we failed completely to capture the global warming seen towards the end of that century. Here, the models were forced with anthropogenic forcings only. They did a much better job of capturing global warming towards the end of the time series, but they actually failed to reproduce what's going on around about here in the 50s. It's only when all forcings, natural and anthropogenic, were put together that the observations are reproduced in so much detail that it can't be just a fluke. These models are so complex. This is telling us that really they're doing a pretty amazing job of reproducing OBS, but also it shows just how much of that warming can be attributed to the human influence. Okay, so a very commonly used measure to make quantitative statements about attribution is FAR, which was proposed in 2003 by Miles Allen, but the concept was around already in epidemiology. For instance, these two distributions could have been something like two groups of people, one of whom smoked and one didn't, and looking at the changing risks of getting lung cancer. So this sort of measure had been used in that way. It was Miles who proposed using it in the climate field. This is actually temperature across the bottom. This is some of Weather at Home data. It's temperature across the bottom, number of models up the side. And this is the natural case here, dotted, and this solid line here is the anthropogenic case. Mathematically, it's pretty straightforward. It's 1 minus Pn over Pa, where Pn is your chance of exceeding this red temperature threshold in the natural world, and Pa is the chance of exceeding that temperature threshold in the anthropogenic world. And as you can see in that case, when these two distributions are well shifted, you can see that you've got much more chance of exceeding that threshold in the human-induced world, in which case your FAR will be quite high. Probably best to see an example. Suppose the risk of any given event, or the risk of exceeding a particular climate threshold, was 1 in 50 in a natural world, and it's changed to 1 in 10 in the anthropogenic world. So it's a 5-fold increase in risk. Plug those numbers into there, FAR pops out as 0.8. So that's saying that 80% of the risk of the event in the new human-induced world is attributable to the anthropogenic influence. So if there's a 5-fold increase in the risk, there's a sense in which 20% of that risk was already there in the natural world, which means that what FAR is saying is that the other 80% is attributable to human influence. And finally, just a couple of headlines to illustrate the sort of information that projects like World Weather Attribution and ClimateCentral.org put out as soon as possible after extreme events. So when it comes to extreme events, increasingly the general public and the media are asking for how much did the human influence on climate affect the chances of this event. And there's more and more pressure on scientists to get those results out very quickly after an event. So some modelling groups, Weather at Home among them, aim to put out these statements very as soon as possible. Of course, papers on the issues need to go through peer review as always, but some groups which have established and already peer-reviewed methods aim to put these statements out as soon as possible after the event. Excuse me. Okay. Right, so just to give you an example now of some of the science that we've done with Weather at Home in New Zealand, and also to see that that FAR in action. I wanted to tell you about a study that we wrote up a couple of years ago. There was extreme 5-day rainfall in Northland in July 14, which caused an estimated almost 20 million in insurance claims. We analysed that with attribution experiments from Weather at Home ANZ for 2014. And it appeared in this supplement explaining extreme events from a climate perspective, which is something that BAMS, the Bulletin of the American METSOC, has published every year for about the last 5 years, with the specific aim of getting papers out as soon as possible about extreme events of the previous year. So this was the synoptic situation in July 14. This was the culprit, an intense low pressure system here, which entrained extremely super moist air from further north. But its partner in crime was this huge high pressure here, which parked itself over the country for about 5 days and just allowed this low pressure system to just keep raining on poor Northland. This tells us, this was plotted by Trevor, and it's NZ land, but I believe it takes into account a lot of observations. So this gives you some idea of the observed state. So you can see this very, very moist air up here. This is total column water and the surface flow, the contours. For comparison, this is from the Weather at Home model. So what I was saying earlier about how it's always super important that we stay rooted in the obs and that we check that our model is doing something credible. This is actually precip. It's not, we didn't have total column water then, but we do now. But the closest we could get was precip, and we were pretty happy to see that it's doing something really quite credible, doing a very good job of reproducing what happened in the event, together with the surface conditions, the low here and the high here. And looking back, just to put 2014 in context, this is the Virtual Climate Station Network observations. So maximum 5-day rainfall totals in Northland from 1972 to 2014. Just to show, 2014 obviously was very much an extreme over that period. Okay, and I've said much of the background to this already, but our 2014 attribution experiment essentially had the black experiments, which were all forcings, the 2014 that was, and the red experiments where we took away the anthropogenic influence in both the forcings and the patterns of SST warming at the bottom. In each case, we created very, very large ensembles by just making a very small change in the initial condition. So in each case, it's given us, that's taking care of like the chaotic variability in the weather. And so it's giving us thousands of ideas of how 2014 was could have been under those conditions, and thousands of realizations of how it might have been without the human influence. And these are the results. So this is rainfall up the side and return period across the bottom. I've got here almost 3,000 of the all forcings, which is the human influence case, and almost 6,000 of the natural in red. And as you can see, generally speaking, the human influence world is wetter. The grey bars are to guide your eyes to where they actually separate beyond these horizontal error bars. So that's where we considered that actually there's really quite a significant change. So the first thing that's telling us is that there was an anthropogenic influence on this event. And that this blue threshold here, which was in our best guess of the model equivalent of the event itself, what was a 1 in 350 year event in the natural world has now become a 1 in 200 year event in the human-induced world. So almost a doubling of the risk of 5-day rainfall in July in Northland. So we computed the FAR for that, just to show FAR in action and how Weather at Home can help us actually make these quantitative statements about climate change and attribution of that. At that blue threshold, we got a FAR of 0.47, so 47% of the risk of that sort of that amount of 5-day rainfall in the human-induced world is attributable to the anthropogenic influence. We also estimated the uncertainty in that because there was a range of values over which our best guess of the event could have been. We got anything from FAR of anything from 0.1 to 0.8 with a peak at about 0.7. So we figured that we could be fairly certain that there was a statistically significant anthropogenic influence on this sort of rainfall. Not over absolutely all the range of uncertainty. So we ended up concluding that most likely the risk of such heavy rain had increased due to anthropogenic influence, but only medium confidence in the exact degree to which that's the case. It's also important to bear in mind that, of course, there may not be an anthropogenic influence on these events, or it may even work in the other direction, that rainfall was expected to get lighter. But in this particular case, we found almost a doubling of the risk of such heavy rain. And this is just to show these were all the events that went into that particular issue of the BAM supplement. Here we are with our rainfall study in New Zealand. But from the very first report to this one, the types of event and the sheer numbers of studies had increased dramatically. So all sorts of other drought, heat, fire, etc., all sorts of other studies go into those reports. Okay, excuse me. Moving on. Another good way in which we can make concrete use of weather at home information. We are currently working with New Zealand Treasury on estimating the financial costs of climate change. I want to just outline here what we did. I probably shouldn't say too much about the actual numbers involved until that report actually becomes public, but I did want to show you how a really neat way of using this information. It was Dave Frame's great idea. I believe Miles Allen had proposed the use of FAR in this way back in 2003, but as far as we know, it was Dave's idea to use it here in New Zealand on these data. As far as we know, it hasn't actually been done before. The idea was mooted back in 2003 by Miles, but as far as we know, this is global first. And Miles is has been very happy to see what we're doing and thinks it's really cool. So we've essentially looked at flood and drought for this. And I've been involved in the flood part of that using Weather at Home precip data. Luke really is our drought expert, but he used other models for that. The basic idea is this: FAR, the fraction of attributable risk, times the total damages, will tell you something about how much of those damages were directly attributable to human influence. So we can begin to get some sort of idea of the cost of the human influence on climate. So we took 12 flooding events in the past decade, and essentially we mapped FAR for the appropriate months and seasons, which was something we were thinking about doing anyway, because otherwise we have to build up our information about rainfall, say rainfall events on a case-by-case basis, which obviously is a little bit slow. So we had already got to the point where we thought, well, let's look at maps of FAR to get a quicker handle on what's going on over the whole country, over the whole year. Trevor used his clever statistical fitting on observations to determine the extremeness of the events, and we then put those two together to actually determine a particular FAR for the event. We then combined that with estimates of the damages which came from the Insurance Council of New Zealand, and put it all together to provide an estimate of the financial cost of climate change attributable to human influence. So, just to show you an example of what we did here. So this comes directly from the Weather at Home data, actually from the 2015 experiments. Here's FAR ranging from -1 to 1, and this is at the 97th percentile of the All Four Things precip, so it's the very wettest end of the distribution of rainfall. So here we see the most highly attributable rainfall changes are here on the west coast, where we getting FARs of up to 0.7, 0.8. So very highly attributable increases in 1 day. This is 1 day extreme rainfall. I chose this example in particular because, Dan, you can see a very consistent pattern down the eastern side of the country. We're tending to get small and even negative VARs. So as I was saying before, it's not necessarily the case that we're going to see increased rainfall everywhere. We've burrowed into this sort of pattern in a lot of detail, and it makes a lot of sense to us. We know that in a warmer anthropogenic atmosphere, we expect the atmosphere to hold more moisture, so we do expect rainfall to be heavier on the whole. But along with that, we also expect systematic changes in the circulation, and we know that one thing we know is that we expect the westerlies to increase across New Zealand. So if we've increased the westerlies and dumped more rain on the west coast, at the same time we're reducing the amount of flow that comes from the east that would otherwise deliver the heaviest rain to the east of the country. So we see this quite consistent pattern of wettening in the west and actually drying in the east. So we sometimes get, we did actually find generally positive VARs, but we do also see for some regions and some events negative VARs as well. So there's a mine of information in these ensembles. Looking ahead, I said I had two sections towards the end. Looking ahead, one of those is about impacts and impacts attribution. So this field of probabilistic event attribution, the way that up to now, it's a field that's developed very rapidly in the last 10 years, and Weather at Home has been a very great part of that, although obviously there are you don't have to have weather at home to do that, but it's been a big part of that. The field has moved very rapidly, but where the field is moving right now is really towards attributing the impacts of climate change as well as the meteorological events themselves. As an example of one of the first studies of that sort, Dan Mitchell last year had a very nice paper in which he actually went right through to quoting the numbers of deaths due to heat wave in London and Paris that were directly attributable to the human influence on climate. One of the most useful impacts models for New Zealand, I'm not an impacts modeller, but I'm trying very hard to make sure that the output from Weather at Home can feed into as much as possible. I figured that crops, excuse me, and hydrological models were probably important. Of course, there are lots of other things as well, storm surge, coastal erosion, and certainly open to any ideas. Troy Basin and Christian Zammit have been very helpful in helping me to understand what output we need to save from Weather at Home to input into these models. But I'm certainly always looking for help to make the maximum use that we can out of this mine of information. And looking ahead again to how extremes might change in the future. This is work that's very much on the go now with Weather at Home, but it's a really exciting opportunity for the future. So up to now, I've talked about attribution and what we can say about how climate has changed up to now, and to what extent the human influence on climate changed that. This is now looking right ahead, so making projections of how weather and particular extremes might change in the future. There are various ways of doing that. There's a project called C20C+, which is aiming to fill that gap by running all sorts of different models many times. But there's a project in the UK called HAPPY, which is half a degree additional warming prognosis and projected impacts, which is essentially looking at extremes in a world 1.5 and 2 degrees warmer than pre-industrial. And that essentially has arisen on the back of the Paris Agreement, which was aiming to limit warming to 1.5 degrees rather than 2. So there's an upcoming IPCC report next year, which wants to be informed about the changes in changing risks of extremes in a world if we were to hold temperatures to 1.5 degrees rather than 2 degrees warmer. by the end of the century. The Deep South is funding me right now to set up Weather at Home ANZ to look at extremes in the 2040s. But right now we've got sort of entrained into HAPPY, which actually is a very similar sort of experiment. But I'm delighted to say that we've actually managed to put those runs out. So those are actually out with the general public right now. They're crunching as we speak. We've got so far, we're coming up to somewhere like about 1,000 runs in each ensemble at the moment. So just to give you a bit more of an idea, this is time across the bottom. This is this century, global mean temperature. This is RCP 2.6 with several CMIT 5 models, and this is RCP 4.5. It just so happens that RCP 2.6 tends to equilibrate near 1.5 degrees anyway, which is very convenient. So HAPPY's taken a decade at the end here to provide forcings, and for 2 degrees it's actually a combination of the two. So these are actually the SST changes that have been supplied. So we're now forcing the Weather at Home model with these SSTs appropriate to the 2090s as they would be under 1.5 degrees of warming and how they would be under 2 degrees of warming. Sorry, I'm finding it a bit difficult to read my watch, but I think it's about 10 past, is that right? Yeah, thank you. And very briefly, just to illustrate how the HAPPY approach is different, normally we're used to starting from emissions and changing emissions and seeing how that changes radiative forcing, how that changes the global response of the climate, and how that leads to the regional response and leads to the impacts. And of course, through that chain, you've got a gradually increasing amount of uncertainty. HAPPY's different in that it's applying the temperature constraint to start with, and then producing these very large ensembles under those two forcings. So looking specifically at the regional response and extreme weather under those two. So that's an exciting prospect for us. We will shortly be delving into those data to find out what they're telling us might be the changes in all sorts of extreme weather in those two, under those two future scenarios, which I think will be extremely useful information that I would expect many people to be interested in. So just to wrap up, I thought I would, sorry, it's a bit of a list, I know, but I thought I should tell you exactly what we've created with Weather at Home ANZ over the last few years. Large, very, very large ensembles which can give us good statistics exist in Hobart for all the following. We've got attribution experiments for various years. We've got ozone change experiments. We've got ENSO experiments. So it's not all attribution. We've got experiments like these which can tell where we can begin to pick apart the effect of El Nino, La Nina, and ENSO neutral conditions. We have a long 30-year baseline climatology with small attribution ensembles for each of those years. And now we've got 1 decade of the roundabout now, which serves as our baseline against which we're going to compare the future experiments. And then this last one here are the other ones which are literally being crunched as we speak. So we've got 1 decade, the 2090s of projections under 1.5 and 2 degrees of global warming. So those, there's an awful lot of data there. They're crunched by the general public. They're freely available to anyone who wants to dive into them. I think it's a hugely powerful experiment which can give us quantitative information about changing climate, how much of that is attributable to the human influence, and how we expect those to change in the future. So I think it's a very, well, I'm biased obviously, but I think it's a really valuable experiment. What would it benefit from? It would benefit probably from more hands on deck. I know that I personally need to, I'm trying to open conversations with the right people about how we get the information out there in the form that people need. At various points I feel I have my hands quite full enough with creating the experiments and analysing the results. And there are certainly lots of papers waiting to be written. But I would certainly like very much to communicate better now with the sorts of people who really need this information. I think it's an absolute mine of information that we should be able to use for the benefit of the country very usefully. And I think finally I will leave you with this slide here, which comes perhaps a little bit just out on its own. But just to let you, just sort of looking at the shape of this area of the field and where we're at the moment, this is when it comes to weather and weather extremes. This is how, across the bottom is how our understanding of the effect of climate change on the events is, and up the side is our confidence in attributing specific events. And mostly what I wanted to bring out from this is that we're actually pretty, we can be much more confident about anything that involves temperature, because we have longer, higher quality records and temperature doesn't vary so much. Anything that involves rainfall is lower confidence because it's higher variability and we don't have such long or good quality records. Slightly unfortunately, perhaps for New Zealand, we're, I think, probably the most useful information for us involves precip. So I think precip's hard, but I think we have to continue to do what we can. And I'm sure there's an awful lot of information we can use very usefully in Weather at Home. And then right down the bottom we have the very small scale events and things like wildfires, which might require more in the way of land surface schemes. So somewhere in here is storminess. So that's just to give you the general picture. Some of the very, very smallest events like tornadoes are probably many years off in terms of how well we can attribute those. But yeah, so I think that's probably just about everything I wanted to say. I hope I haven't gone too wildly over time, but thank you very much for listening. And I hope I did manage to convince you that Weather at Home is a great tool for these sorts of considerations. Thanks.
Thank you, Suzanne. I'm hoping that the other hubs and participants around the country can see us. We only have a slide of Judy Lawrence, but assuming that's the case, we've got about 10 to 15 minutes for questions. We've turned on the mic here in our Victoria University room, but you just raise your hand on the Zoom room screen. Do we have any questions? Actually, we have a question from Greg Tooson. I'll unmute Greg.
Hi, it's Inga Smith here. Inga Smith here from the University of Otago. So that was a great talk. Thank you, Suzanne. It was very interesting. So I noticed extreme snow and ice was on that graph as reasonably low in the confidence of attribution. Coming from Dunedin, obviously we have an interest in extreme snow and ice down here in terms of the impacts it has on the city. We shut down. Obviously agriculture, it's important as well. Do you have any plans to look at snow and ice at all with Weather at Home?
That's a very good question. Personally, no, I hadn't really got that far. Andrew Mack is in the room. I'm looking very hopefully at Andrew, wondering if he has anything to add to that. Personally, I'm just trying to think. I'm ashamed to say I'm not even sure. Go ahead, sorry.
We talked about, in the Deep South Symposium, we talked about possibly trying to create an attribution strategy. Do you want me to, have to come up?
Sorry, Dave's just coming up.
At the Deep South Symposium, we talked about, Adrian McDonald and Sue led that discussion, but there was a discussion of a possible attribution strategy for how we might go about trying to, I think, capture exactly these sorts of concerns and put together a proposal for an integrated strategy for working our way down that very nice slide. Because there's a whole bunch of different things that people are interested in that I think we could, if we get them on a list and then look at the, capabilities, constraints and impacts of the impacts, we might be able to work towards something. But right now, in terms of we're partly limited by the resource, which is 3 days a week. Hopefully that'll change.
Thank you. A question from NIWA Wellington. I'll just unmute you. Can you unmute yourselves, NIWA Wellington, Lucy? I don't seem to be able to. Here we go. I know.
Can you hear us now?
Yeah.
Yes.
Hi there, this is Johnny Williams. I just got a question on the relation between FAR and financial impacts as relating to insurance claims and stuff. It just seems to me very simplistic to just linearly correlate FAR with financial damage. I just wondered if you could comment on that.
Well, Dave is about to run to the microphone yet again, but first I'd like to say, yes, it certainly is extremely simplistic, but I think possibly we're doing the best we can, and I think the information is there, and we have to start somewhere. We know that I think I'm right in saying the estimate of the costs itself is extremely imprecise, and of course the information that we've got will be imprecise too. But I think yes, it's a crude measure, but we have to start somewhere. One thing I meant to say at that point was that actually there is a slight difference in the nature of those costs. For flooding, it's simply the insured losses, but for drought it was more a measure of the cost to the economy overall. But yes, it's a simplistic estimate, but it's a first go with useful information, I think. Anyway, I'm sure Dave can say something.
Well, the Treasury, we did it with two sorts of different information. One was Treasury's own estimates, or Treasury's commissioned estimates of the economic impacts of the droughts. So they actually try and do a full kind of economic picture of the costs and benefits of those droughts. And in the case of the insured losses, we just tallied up insured losses, so they were very simple numbers. What we're doing in the report is writing a Pathfinder report to show the capabilities of this sort of approach, and to show that we can actually answer these questions, ask and answer these questions. It's absolutely written. The first thing I did was, before we even had the numbers from Sue and Trev and the gang, was to write 2,500 words of caveats, because we know a lot about what the report isn't and what it can't do at the moment. But we think it's the sort of thing we could work towards that would be really, really useful. But in this case, we've just taken other people's numbers and used them as inputs. And those numbers in that great slide of the dollars times the FAR, either of those left-hand terms can be negative or positive. So in this case, we chose numbers that happened to be positive in terms of costs, but you could also apply it to negatives as well. So you could look at the FAR of benefits, and you can have negative FAR of negative costs as well. The inputs can be simple or they can be complex. It depends which ones you pick, but the point is the FAR can be multiplied by a number of different variables.
We have a question from Dan Schwartz, the Ministry of the Environment. Can we hear you, Dan?
Yeah, I'm here. I'm here with 4 others at the Ministry for the Environment. Thanks very much, Sue. My question is also really about the intricacies of FAR and risk. So the first is that in some ways FAR is misnamed, because it's actually fractional attributable likelihood, not risk, and the two are conflated often, but particularly as we move towards trying to manage on the basis of risk there are two things that actually separate likelihood from risk, and one is the damage function, which changes the more extreme the event, that you might get quite a different, not a linear relation to cost and whatever the event is. And the other is that in moving from your natural to your all scenarios, you actually change the distribution of events within that space as well. So it's not just an amplification of the pattern that's there. It's a changing, could very well be a changing one. So yeah, it's real. I'm not I'm acknowledging your answer to the previous question, that this way of costing is preliminary and you're starting with something. I think the background to this is that we are trying to seek a much greater common understanding about what is meant by risk and changing risk, and actually the fractional attributable cost is closer to what we mean by risk in the current understanding. So yeah, it's going to be hard to talk about these things with everybody.
Yeah, certainly it sounds like I'd be very interested to talk to you further about that, and I expect you probably have a much deeper understanding of risk in that sense than I do. But you're right, there are all sorts of objections, if you like, to what we've done, or that it's highly simplified in many ways. And as you said, one of those is exactly how we have to boil the meteorological event down to something we can work with. But it's certainly true that when we look at, say, the change in risk of 5-day rainfall, as you said, that could have been delivered through different events and different methods. So it's hard to nail down exactly the best approach to this. I think I'd welcome a conversation with you to understand further about that. But I think it's an initial first go that probably does that has merit. Certainly, I'm sure there are many ways in which you could make it better. But it's an initial first go at something, and as far as we're aware, we're the first people in the world to have a go at that. So good for New Zealand, I say.
Yeah, if I can just butt in and say, yeah, we're acknowledging the complication, we are really excited to see this as the first example of such work. Yeah.
We just have time for one more question from Judy Lawrence. Judy, can we hear you?
Can you hear me?
Yeah.
Yes.
Okay. Thanks very much, Sue. A super talk, and I never knew what FAR was before, and now I know. So thank you very much for simplifying for mere mortals like me. My question was a little bit related to Dan's question, which was you didn't indicate the time frame over which the costings were done. And I assume it was something in the order of like 1970 through to 2014 or something like that. That was my first bit of the question, and whether or not the methodology can be used to work with projections across a range of scenarios. That was another part of that. But I had I'm going to hop in with another one, which is really about adaptation studies and the need to know whether we can expect more frequent of the sort of more intense, high intensity rainfalls, that sort of area, because we have a number of different statements being made, and you have indicated the attribution of those and deconstructed that story, which is incredibly useful. But the question is, are we going to get more high intensity rainfalls? Can I take that from the various outputs that you have shown today?
Okay, I'm trying to remember all three parts, but the first part, I'm sorry, I obviously glossed over that too quickly. We looked at 12 flooding events in the last 10 years. So they were 2007 to 2017. it was the 12 most expensive events as given by the insured losses. And there were 2 droughts in that period as well that were included. So I hope that, does that clear up the first part?
Yep.
I'm forgetting for a second what the second one was, but the third one was about adaptation to future extremes. Certainly with these ensembles that are out and crunching at the moment, we will be able to say something about how we expect extremes to change in future. We need to probably nail down the most efficient way to get maximum information as quickly as possible. So with the attribution experiments that are already available, we've tended to look at look at things on a sort of case-by-case basis at each event, and that's it's painstaking work, but essentially to some extent there's no way around that. So you do tend to have to, look at the event itself. But we will be able to make, if we choose something like the rainfall duration and the location and the time of year, then there's no reason why we shouldn't be able to make statements about how we expect those to change in the future.
And yes, the numbers are all positive. So yes, we do expect more.
And yes, and Dave is reminding me that generally the numbers are all positive. So if you want a really broad brush statement, you would say, yes, we do expect more high intensity rainfall in a human influenced world. And I don't see any reason why we wouldn't expect that in the future, but I haven't actually looked at those results yet. Hang on, I can't hear you.
Okay.
Sorry, Judy, you've been muted. The buzz is gone. Just to say thank you very much indeed for your precious time. I hope it was useful.
Thanks very much for coming, everyone. If you want to be added to our mailing list to receive notifications of these events in the future, send me an email. It's on that chat room. And have a great day.